Yeah? Okay, fully charged. Thank you. Alright, so so in the last recording, just for the sake of the audience, there were some parts which were silent, so sorry about that. Luckily, those were the easiest parts, and I wrote down pretty much everything on the board, so hopefully the silence is okay, although it looks very strange. I'm just talking and now there's no sound. But anyways, makes for some humor, I guess. We need that. So let's continue the proof of the theorem, which says that every minimal class of order cardinality 3 or more contains an even 2 cut, right? So if I have a minimal class that has at least 3 edges, then there is a pair of 2 edges that comprise an even 2 cut of the given matching code graph, right? And what we observed last time, just do a quick recap. We observed that the bipartite case and bricks are actually easy in a sense. Of course, the bricks case requires a better understanding of mutually dependent edges. The bipartite case is actually quite straightforward. 2 edges, 2 distinct edges, if they are mutually dependent, then actually they comprise an even 2 cut. And in fact, in this case, the converse is also true. If 2 edges comprise an even 2 cut, then they are indeed mutually dependent edges. Maybe I'll just make a note. Okay. Converse holds if the 2 edges comprise an even 2 cut, then they are actually mutually dependent in this sense. Yeah. Okay. So clearly the theorem is true. Converse holds for all matching code graphs. That is correct. Good point. Yeah. Converse holds for all matching code graphs. If 2 edges comprise an even 2 cut, then in any perfect matching, we will either use both of them or neither of them. Therefore, they are mutually dependent. Converse holds for all matching code graphs. Thank you. Good. And in the case of bricks, right? So this in particular implies this result, because any 2 mutually dependent edges will comprise an even 2 cuts. Therefore, you are done. In the case of bricks, what we did is we showed that the hypothesis basically never holds. You just cannot have, forget minimal class, you can't even have an equivalence class of cardinality 3 or more. Cardinality is always 1 or 2 in the case of bricks for any equivalence class, right? And this we proved as an easy consequence of this, and we used the fact that the symmetric difference of 2 cuts is a cut, right? That was nice. So that we are done with that. And then we started the proof of 8.17, and so we are done with bricks and bipartite graphs. So we may assume that our matching code graph G we may assume all of the following. First of all, G has a non-trivial tight cut. Yeah. And additionally, we also made an observation. We basically thought about how dependence, in particular how minimal classes, sort of behave across tight cuts. And so the proof is by induction on the order. As are most proofs in life. So we also observe the following, that if C is any non-trivial tight cut, then the minimal class Q that we are considering looks like this. Supposing this is my cut C, then in fact Q has exactly 3 edges, and the 3 edges look like this. One's here, one's here, and one is here. In all other cases, we are able to finish the proof by induction. Okay. So I should probably write G as a non-trivial tight cut, and the cardinality of the class is exactly 3. That's the only case where we are not able to finish the proof by induction. And if my Q is the pink colored set of edges, so and let me also give some notation. Let's say Q is E1, E2, E3, right? Then the 3 edges of Q look like this. Yeah. In all other cases, we finish the proof by induction. Yeah, everybody okay with that? So therefore, we are left with this case. Having made these observations, we invoke theorem 8.13 on E1 and E2. Yeah. And we get a drawing like this. Basically, I'll just maybe I'll just change the drawing here. So instead of E1, E and F, I'm not going to make it E1 and E2. I should have probably done this in the beginning. Anyways, not too late. E1, E2. Good. So, with a small dose of laziness, we are here. Right? This is the situation. Yeah. And now we make use of this observation. For any non-trivial tight cut, the 3 edges E1, E2, E3 look like this. We make use of this to conclude that all of these components are either trivial or exactly one of them is non-trivial, and that fellow contains the edge E3. Right? If 2 non-trivial components, then you will see that this is violated for one of the cuts. So we can now conclude that in fact we have something more restricted. The situation actually looks like this. So now this is not theorem 8.13. This is applying it to whatever situation we have. This is the edge E2, and there is an edge here. Maybe I should draw this a bit bigger. The non-trivial odd component is really non-trivial. This is our E1. This is E2. And this fellow here is E3. And we can call this component K. So this is where we were at. Well, we actually proceeded further. We considered case 0 when K is also trivial. Yeah. Yeah. In which case we don't know where K is actually. Right? It is only in the case when we have a non-trivial component we can say that the third edge has to be here, and therefore all other components are trivial because there is only one third edge. Right? But if we don't have a non-trivial component, then we cannot apply this observation because we don't see a non-trivial tight cut in the figure. Right? Okay. So yeah, so maybe I'll just write down case 0 here. case 0, all components are trivial, in which case we don't have this drawing, we have the all trivial drawing. All components of G minus E2 minus B are trivial. Okay, so then we make another drawing for that case. This is our B, we can call this A, and the graph is basically bipartite if we delete E1 and E2. Okay. And we considered the graph H, which is G minus E1 minus E2. And we made a few observations. Since E1, E2, E3 is a minimal class, it is a class by itself. The only unmatchable edge in this is E3. Every other edge is in a perfect matching because it's a minimal class and we did not delete one edge, so that fellow is unmatchable. So E3 is the only unmatchable edge of H. That means H is basically two bipartite matching code graphs and you have added one edge. One more observation we could have made in the beginning: if we delete E1 and E2 and we get a disconnected graph, then we are already done. Then it already means that E1, E2 is an even 2 cut. E1 follows because of mutual dependence. Right? So if G minus E1 minus E2 were disconnected, you are already done. So that's another point. We can also assume that H is a connected, matchable graph. Yeah. So that means H is just two matching code graphs bipartite, and we have added one edge. So actually the graph looks like this. We can draw it in this way. This is our H fellow, and I will actually put some vertices to indicate that they are equicardinal sets, these two and these two, and the edge E3 goes like this. This is H. There are no other edges in this cut in H. And at this point, I was talking to Santosh, and actually there is an even simpler argument than what I said last time, I think. There is an even number of vertices on the left side, even number on the right side. Therefore, every perfect matching in the original graph meets this cut in an even number of edges. Because I have only removed two edges, it has to be E3 and one of E1 and E2. All three cannot be here because then I will have a even cut meeting a perfect matching in three edges. That's a contradiction, right? Even cut has to meet a perfect matching in an even number of edges. Therefore, one of E1 and E2, without doing any further analysis, we can conclude that one of E1 and E2 is in this cut in the original graph G, and the other one is not. Therefore, one of E1 and E2 and E3 is an even 2 cut. Right? Last time I was looking at the bipartite and doing some counting. None of that is necessary. We don't even need bipartite. So we can actually simplify further and simply conclude one of E1 and E2, exactly 1, plus E3 is an even 2 cut of G, and therefore we are done. This is what we wanted to prove. Yeah? Good. So that settles this case, which we had already settled last time. So this was all just background work. And now we go to the case that we hadn't settled. We have a non-trivial component. So we are now in this case. This is our case 1. This case requires a little bit more work. And in fact, I would like to know if we can make that lesser. But yeah, let's see. Questions, concerns at this point? All good? Everything is clear so far? Yeah. Okay, so we need to settle case 1. Well, you kind of can guess what we will do. We will look at this tight cut, this non-trivial tight cut that is staring at us, and we will consider the 2C contractions, at least one of them, if not both. Yeah? So that's what we'll do. We will take the component K, we will shrink everything else into a single vertex, we'll look at this graph and do something with this graph. So, maybe I should, I will erase some of these things. I think you all already know this, so I don't need all of this content here. Okay. In fact, let me also erase this. Okay. Okay. Good. So let's consider the graph obtained by shrinking the complement of K into a single vertex. We'll call this vertex little k bar, and there are some edges. I don't know how many, but I know that there is E2. This is going to be my E2. Let us also give labels to the ends of E2. Let me call this fellow little x. Let me call this fellow little y. So this fellow is little x. Yeah? And the edge E3 has both its ends over here. Yeah? That's our graph. I don't know what to call it. Maybe I'll call it G1. Yeah. Okay, so we have a smaller matching covered graph, and E2 and E3 are mutually dependent in this graph, right? We observed that for a non-trivial tight cut, if you consider the two contractions, then the dependence relation of the contraction is simply the dependence relation of the original graph restricted to the contraction Z set. Okay, so therefore, E1 and E2 are mutually, E2 and E3 are mutually dependent in this graph. Yeah. So we may apply once again 8.13 to these two edges in this graph. Yeah. The question is, which fellow do I put in the barrier? Which fellow do I put in the odd components? I want the contraction vertex to go in the barrier, so I will take E2 to be in the barrier. Okay, so 8.13 applied to the graph G1 and the edges E2 and E3. So, in the graph G1, there is a barrier. I don't know, 4. Let me start with the most general figure. There is a barrier, I don't know, I'll call it B1, why not? The edge, I want the contraction vertex to go into the barrier. So therefore I'll take E2 to be here. I haven't tried the other way around. You could try it and see if you can finish the proof like that. I'll take E3 to be here. Yeah? All good? So the ends of E2, we know that they are x and k bar. So let me put x here, and let me put this contraction vertex little k bar over here. Yeah. All right. Okay, any questions, concerns, all good so far? Yeah?
So here, can we choose B to be maximum?
Can we? Yes, I think we can.
Then K bar does not belong to any nontrivial barrier in the graph G1.
You want to choose B to be maximal. If you choose B to be maximal, then what's your claim?
K bar does not belong to any nontrivial.
So your point is that you will now get a larger barrier in the original graph using this figure. Is that correct?
Yeah.
Essentially what you are saying is that you can see, you may not have written it down.
No, I'm using this G minus U minus V is maximum if and only if there is no barrier.
Okay.
So this odd component K should be factor critical.
Okay.
Which means, which is the same as G1 minus K bar. And
minus any other vertex not having a perfect match.
Yeah, minus any other vertex should have a perfect match. Therefore, K bar and any other vertex do not belong to any nontrivial.
Okay, so let's see. So your point is that let's choose B to be a maximal barrier in G with this situation. And if you had chosen B to be maximal, then we would basically get a contradiction here. Is that your point? Yeah, actually that's a good point. So in fact, let me write it the following way. Is it true? So in fact, related to your question, let me not fully answer the question yet, also so that everybody has a chance to think about this point. Is it true that you can actually see a larger barrier in G? So that's my quick DIY. Here's a DIY. Can you find a larger barrier in G that includes the original B as a set, as a subset? Oh, good. Yeah, actually that's a good point. G
Not a barrier. G minus E2.
G minus E2. Or is it G minus E3? Yeah, good point. Let's see. Anyway, I'm going to leave it open-ended. G minus E2 or E3 or something like that. And then we'll see how to finish the proof using your idea. right? So I don't know, G minus EI for some I don't know. That includes B. Okay, think.
That is open. Applying 8.13 to which edge is also open.
Oh yeah, everything is open. Okay, see if you can think about this. Can you find some larger barrier in G minus one of these three edges, E1, E2 or E3, I don't know, pick your edge that works for you. And see if you can find a larger barrier, which means it is a proper superset of B. And you want to use these drawings and maybe make more drawings. I'll give it a name anyways, B star. So see if you can figure out what B star is and what EI is. So what I would suggest is, if you are stuck, just guess this. This is not too difficult to guess if you have seen some similar proofs. For example, one thing that we prove is if you take any maximal barrier in any graph, is that correct? Then all the odd components are hypermatchable. Is that a correct statement? Yeah. Do I need any qualifiers? In any graph, we go to the SGT definition of barrier, right? The more general definition of barrier. In any graph, you take a maximal barrier. G is your graph, B is a maximal barrier. Then all odd components of G minus B are hypermatchable. Factor critical, right? I don't think we need even matchable graph. This works for all graphs. Yeah. Because if the component is not hypermatchable, then you can delete one vertex there, and now you will have a graph that is not matchable. You take a touch set there, and now you take the touch set along with the vertex and the original barrier, and you will get a barrier again. Something like that happens. Yeah. So anyway, so the point is, if you have seen proofs like this, then just use those experiences to guess this set. Once you guess this set, then you can figure out what is the edge EI and all that. So try to guess B star. At least that is how it works for me typically. What would be a reasonable B star to guess? Maybe just write it down and I'll come and check. Maybe there are multiple things at work, I don't know. Right, so I'll give you a hint here. Guess B star using B and B1. Okay, so I'll just tell you what B star is, and now you can think about what EI is. So consider this B star. take B, take all of B1. Observe that B and B1 are actually disjoint. There is something that bothers all of us is little k bar. Well, forget little k bar. B and B1 minus k bar are disjoint, and they are all original vertices of the original graph G. Yeah. So we will take that B union B1 minus the contraction vertex. Consider this fellow. Of course, I have not told you what EI is. See if you can figure out EI. I claim that this is a barrier. This fellow is a barrier in G minus EI. What is I? Right. And let's make sure we have an idea about what these graphs are. So this is the G, and these two here are drawings of G1 on the left and the right. And in some sense, the one that is really useful are these two. Using these two, can you figure out what EI is? And if you have already figured out, then try to see how to finish the proof in multiple ways. Looks like different folks have different arguments to finish the proof. And I'm not fully convinced how many of those are correct. I know one of them is surely correct, but the other two I am still figuring out. Hopefully we will all figure out by the end. If you make a drawing, you will actually guess EI quite easily. Yeah, if you just draw things out, it's quite clear what I is. Right? EI should not have ends in the barrier. Both ends of EI must be outside the barrier. X is already in the barrier, B. Well, X is already in the guessed barrier. We are yet to prove that it is a barrier. We haven't proved it, right? So X is already here. So therefore, X is an end of E2. Therefore, EI is not E2. And B contains the ends of E1. So it still contains the ends of E1, right? Graphs don't change, at least not in this course. Right. So therefore, EI is E3. Now let's prove this claim. Let's observe that this is actually true. So E2 has an end here. I'll just draw E2 like this. I don't care where it goes right now. E1 has both ends here. I've moved things around in my drawing, but at least the number of vertices is the same. Let's look at this drawing and let's pay attention to one component. This fellow has all its neighbors in B. Therefore, this fellow is still an isolated vertex in G minus B star, right? Because I'm deleting all of B. So therefore, this fellow is still going to be isolated if I delete B star. Yeah? Is that right? Okay. Observe that all the odd components here, in fact, these vertices don't even exist in G1. You don't even have to worry about G1. These vertices are gone in G1. They all have become little k bar. So if you are worrying about, oh, what happened to this vertex here? Well, it's not here. Right? These vertices are all in G but not in G1. All their neighbors are in B, therefore all their neighbors are in B star. So they are still isolated. Let's look at this Y fellow. All neighbors of Y, with the exception of X, are in B. X is in B star. It's on this side. Therefore, Y is also isolated in G minus B star. And Y also does not exist in G1, by the way. Yeah. So all these fellows, 1, 2, 3, 4, let me put them here. And one of them is Y. Y is going to X. Okay. So maybe I should have put X here only. Give me a nicer drawing. I'll put X here. This is the edge E2. Yeah?
We can just imagine getting this drawing by replacing that circle with the new drawing of G1 minus K1.
Sorry?
So you take that drawing of G, delete K,
Okay.
and replace it with G1 minus K.
Yeah. There are many ways to go from here to there. I'm doing it in the simplest way possible, right? I mean, I'm doing it in the sort of, this is not simplest, this is actually more work what I'm doing.
Yeah. That's why
But sometimes more work is helpful, right? Yeah. So yeah, there are ways to get here faster, but I'm deliberately taking a longer route. Right? I just want to make sure that we grasp all the nuances. Right? Yeah. Okay, so these are fine. Now consider these fellows. These are odd components in G1 minus E3 minus B1, right? And observe that if I look at any one component, let's consider J for a moment. Where are all the edges from J going? They are going into B1, which includes this little k bar fellow. But little k bar is what? Little k bar is basically all of this stuff, right? And convince yourself now that in fact they are all going into capital B. All edges from J are either going into B1 or they are actually going into capital B. All these edges in the cut, they have their other end here, except for E2. E2 we have already drawn, so you can forget E2. So all edges in this cut are going from this component into capital B. Therefore, all edges from J in G minus E3 are going from here to either B1 or into capital B. Yeah? Which means all these four, if I delete E3, then all these four, all the neighbors are being B1 and B. Therefore, all these four, they look like this after I delete E3. Yeah? But E3 is of course joining two of them. Right? And what Santosh is saying is, we could have simply taken this and replaced this fellow by all of this stuff. That's basically what we got here. Yeah? Yeah, it's just that drawings can also be misleading. So it's also good to be careful and check that you didn't make a mistake there. But yeah, once you have seen enough of these things, then you just start seeing them much faster. Okay? Okay? Are you all convinced that this is a valid drawing? We are not lying to ourselves, we are not fooling ourselves. B star is indeed a barrier in G minus E3 minus, yeah, G minus E3. Yeah. Okay, so we got this drawing. Now there are multiple ways, it seems. I am yet to convince myself that all of those ways are valid. So we can do it together. So let's try to finish the proof from here in 3 different ways. So one is to observe that we got a larger barrier. It's larger than B because we included B1 minus K bar, and B1 has at least 2 vertices. There is at least X and K bar. So therefore we have added at least one more vertex when we went from B to B star. So we have a larger barrier, and it is tempting to say, hey, there's a contradiction. We could have just taken a maximal barrier and the proof is finished. Now we got a larger barrier. But there is a catch, right? EI. Barrier in which graph? Right? These are not barriers in G. They are all barriers in G minus EI for some I. Right? So we have to be careful. We can't just say we have a contradiction to maximality. We have to be very careful in our choice of the original B, and then we can contradict somehow if we choose it carefully. Yeah. So does anybody see a way to complete it? Is there a way to complete it, or is it not possible to do it using this maximality argument? Okay.
So like you can choose the barrier in either G minus E2 or G minus E3 containing E1 of the largest size.
Right.
So like there are some set of barriers containing E1 in G minus E2. There are some set of barriers containing E1 in G minus E3. You can choose the largest among
Containing, yeah, exactly. Right. So what Amit is saying is, we know that theorem 8.13 applies to G and EI EJ for any choice of IJ, right, between 1 and 3 not equal. Right, so we could apply theorem 8.13 to any of them, and we know that in G minus EI there is a barrier containing the ends of EJ. Right, this is true for all distinct I, j between 1 and 3. So one way to finish the proof would be to say that amongst all barriers of G minus E2
or G
containing the ends of E1, union all barriers of G minus E3 containing the ends of E1, choose one that is as large as possible. Right? And if we choose one that is as large as possible, then we have a contradiction and we are done. In fact, we can simplify it further. We can just say among all barriers of G minus EI containing the ends of EJ, where J is not equal to I, choose one that is as large as possible. No need to tie ourselves with 1, 2, 3. Right? Among all G, EI, EJ, or rather, yeah, you get the point. EI, EJ, barrier. Choose the largest barrier possible. And if we had done that, then we would simply say that, well, we have a larger one for some other choice of I and J, therefore we have a contradiction, proof is finished. Yeah? Is that correct? Does anybody see a mistake in this? Does that seem okay? Does it okay? Seem okay? Yeah? Yeah? Works?
Now I'm wondering, what if we did this before even concluding QS3?
Sure.
As the first one. But
Yeah. So the question Santosh is saying is, was there a way to do this even before concluding anything about Q, cardinality 3 and all those things? Is there a way to make the proof even shorter just using 8.13 and skipping all those other things? Try it, give it a shot, see what you get. Yeah. Hopefully we'll have some activity on Piazza finally. Yeah. Good. So that's one point. That's one way to complete the proof. Anybody sees any issues with this proof, with this approach? No? Okay, good. So we have something to send to Claudio. Let's see if we have more. So now, are there any other ways to complete the proof? You had an idea about hypermatchability. Yeah. So Santosh's point is, it seems even probably even faster, or at least in some sense, doesn't require all this complicated choice and all that, right? Which takes a few words and all that. So what Santosh is saying is, we know that in G minus E2 there is a barrier containing the ends of E1. Is that right? Now just take a maximal barrier in G minus E2 that contains the ends of E1. Because it is maximal, all the odd components are factor critical. Right?
Yeah, it does not follow from what we proved in SGT. We are restricting ourselves to barriers containing E1.
Oh.
So you have to repeat.
You have to work a bit. Yeah, you have to basically, because the barrier just becomes larger. So yeah, okay, I see your point. So what Santosh is saying is, you take a barrier of G minus E2 containing the ends of E1 and choose one that is as large as possible. Choose a, right?
Yeah, maybe.
Yeah, choose one that is as large as possible, or just maximal. Maximal probably just works. And now you conclude using this choice that K is actually hypermatchable. If it is not hypermatchable, then you can take some vertices from here and add them here and get a larger barrier, which will again contain the ends of E1, therefore a contradiction and all that, right? So now this will be hypermatchable. Therefore, if I delete the contraction vertex and any other vertex, my graph is a perfect matching. But that is contradicted here because we have a barrier containing the contraction vertex and some other vertex. Yeah. So if we choose a maximal barrier in G minus E2 containing the ends of E1, then all odd components of G minus E2 minus B are factor critical. In particular, K is factor critical, right? Therefore, in the graph G1, if I delete the contraction vertex, little k bar, and I delete some vertex from K, then I should have a graph that has a perfect matching. But that is contradicted here because we have a barrier containing k bar and x. Yeah.
Why can't x go into the maximal barrier?
Why can't
X go into the maximal barrier?
x go into the maximal barrier?
No, we are.
No. So the point is, in G minus E2, we know that there are barriers containing E1, so that's a good point. In G minus E2, there are barriers containing the ends of E1. So let's draw one such barrier. This is some barrier in G minus E2 that contains the ends of E1. But in the original graph, there should be no stable barrier. Unstable barrier. We know that the original graph G is matching covered. So therefore, when I add back the edge E2, I must kill all non-trivial, all unstable barriers. Therefore, the edge E2 has its ends here, and therefore X, Y are indeed not in the barrier. Right? So X therefore cannot be in a maximal barrier of G minus E2 that contains both ends of E1. Right? Then we get an unstable barrier in the original graph. So yeah, good point. Yeah, everybody's okay with that? So therefore X and Y will not go into the barrier. They will be in odd components. Yeah?
So you're deleting the contraction vertex and its neighbor,
Yeah.
and you're claiming that the remaining graph does not have a perfect matching. How does that follow through? Oh wait,
Sorry, can you repeat that point?
So you're taking the contraction vertex
Yeah.
and the neighbor in the barrier,
Yeah.
which is X itself. in
Yes.
A.
Yes.
So you're deleting these two vertices,
Yeah.
and in the this diagram, we are basically deleting the two vertices from the barrier.
Yeah.
So why does the remaining graph does not have a perfect match?
Oh, because this E3 is still there. Ah.
No. So that will be a perfect match in containing E3, not containing E3. Sorry. No.
Yeah, that's a good point. I think I forgot the edge E3. The edge E3 is there. Yeah, this is not a barrier
That's true.
if we keep E3 in the picture.
That is true.
Yeah, okay, good. Right, so looks like we are not done yet. Yeah, okay. So anyways, so maybe you should think more about this. Right, good. Okay, so maybe the second approach doesn't work yet. But it might work, it's more work. Good, okay. So choosing this EI, EJ, B, that seems to work. Just using factor criticality and finishing it, we found a bug there. Good, great. So now let's look at the actual proof in Lucchesi Murty, which is also what Manoj suggested. So what Manoj's point is, look at this drawing. Right? This is an honest drawing. Now observe that by the same arguments as before, we can conclude that all components are trivial. All components, here anyways they are trivial. We had already concluded once upon a time that they were trivial, so they remain trivial. These fellows are also now trivial. If any of them is non-trivial, now even if one of them is non-trivial, it doesn't enclose one of the three edges E1, E2, E3. All E1, E2, E3 are outside the odd components. Therefore, we can conclude from this drawing that all these fellows are trivial. Otherwise, we are done by our observations here. This drawing. Let me draw the pink edges. Right? Let's draw the pink edges. We can see where all the pink edges are. E1 is here, E2 is here, E3 is here. None of these components can be non-trivial. This proof is finished by induction. Therefore, all components are trivial. And now we are in case 0 for a different choice. So all are trivial. This is a situation, and G minus E1 minus E3 is now bipartite. We are now in case 1 for E1, E3. Did not work for E1, E2, works for E1, E3. So therefore we are done. Yeah. So there are at least 2 ways to finish the proof, and this is the way that is actually used in Lucchesi Murty. All right. Questions, concerns? Okay, so conclusion is that we are done with this. Every minimal class of cardinality 3 or more contains an even 2 cut. This means, corollary 8.18, every removable class is either a singleton or a doubleton. We had already restarted this chapter by noting this to be true for bipartite matching code graphs. Every removable class is a singleton. Now we have a statement for all matching code graphs. Every removable class in any matching code graph has cardinality 1 or 2. Henceforth, for removable classes of cardinality 1, we will call them removable singletons or simply removable edges, which is where we started the entire thing from. And for cardinality 2, we will call them removable doubletons. Yeah? And this singleton doubleton is simply a reflection of the eventually to come ear decomposition theorem, where we will prove that either you add a single ear or you add a double ear. But now you have to talk about ears, whereas here we are just talking about edges. But they are basically nothing but one and the same thing. Yeah. So we can take a break here. I haven't really thought much about part 2, but I have an idea. Let's see an application of all of this. Right? Basically, I'll talk about some of the things we already discussed earlier. We'll see some of Narayana's results in the light of these things. Yeah, that's probably one of the coolest and simplest application in some sense of some of this theory that we are seeing. Okay, thank you.